Watch this digital cloth tear under tension. We are looking at rapid, continuous change calculated frame by frame. In a completely different environment, consider an electronic circuit board. Here, change is invisible, taking the form of a rapidly oscillating transient current when a switch is flipped. Finally, observe a satellite in low Earth orbit, where gravity governs massive shifts in velocity and trajectory. Though visually distinct, these systems share the exact same mathematical architecture. They are driven by differential equations, expressions that directly connect an unknown function to its rate of change. In early calculus, finding a solution meant evaluating simple, isolated integrals. In real-world engineering, those isolated math problems do not exist. Systems are dynamic, and variables constantly influence one another. To model this reality, we have to start by dissecting the structural anatomy of ordinary differential equations, specifically identifying their order and their degree. Once those definitions are locked, we will map them directly to orbital mechanics, circuit design, and physics simulations before verifying the math programmatically in Python. Mastering these strict mathematical definitions is the mandatory prerequisite. You cannot predict or control a physical system until you can accurately classify the equation that governs it. A differential equation maps the internal derivatives of a physical system. To solve one, you first determine its boundaries. This equation contains multiple terms, but its order is defined by the highest derivative present. Look at the highlighted term. Because the second derivative is the highest, this is a second-order ordinary differential equation. The first derivative term is irrelevant to the classification. Once the order is established, we look for the degree, which is the exponent or power of that highest-order derivative. In this equation, our highest derivative is raised to the power of 3, giving it a degree of 3. There is a critical mathematical condition here. It only has a defined degree if it can be expressed as a polynomial in its derivatives. This leads directly to the edge case that traps many engineers: derivatives locked inside other functions. Take a look at this equation. We have a first derivative trapped inside a cosine function. Because of that transcendental cosine function, we cannot extract the derivatives into a clean polynomial. Consequently, the degree of this equation is strictly undefined. Proper classification is not academic trivia. The order and degree dictate the algebraic methods available to you and directly represent the structural complexity of the physical system you are trying to build. This family of curves represents the general solution, all possible theoretical states. Overlapping waves exist because integration leaves arbitrary independent constants. Varying c slides the wave along the y-axis. The quantity of these constants perfectly matches your equation's order. A second-order equation yields 2 constants. But engineers do not build systems based on infinite possibilities. We require a particular solution, a single exact reality. To find a particular state, extra curves fade away as we lock on to distinct coordinates. We assign exact values to those arbitrary constants, derived from initial conditions. In physics, measuring exact starting position and velocity pins the math down, predicting a single true forward path. The general solution defines the universal laws of the system. The particular solution dictates the exact actionable event we are engineering. Aerospace engineering relies entirely on finding these precise analytical solutions. This visual maps Newton's law of universal gravitation. It's a second-order differential equation. Its general solution contains all possible orbital conics, elliptical, parabolic, and hyperbolic trajectories. By applying boundary conditions, the satellite's exact launch velocity and altitude, we isolate the particular solution, confirming a stable elliptical path. We see the exact same process when moving from the macro scale of space to the micro scale of circuit design. This schematic outlines an RLC circuit. The entire electrical flow is governed by this second-order equation, matching the hardware perfectly. The circuit contains 2 energy storage components, inductor and capacitor. The particular solution tells us exactly how current oscillates and decays the millisecond a switch flips. In analytical fields, engineers rely on resolving general solutions into particular solutions to plot continuous, unbroken physical behavior. Computing engines and real-time physics simulators operate under completely different constraints. They cannot rely on absolute, unbroken curves. When hundreds of objects collide simultaneously in a modern game engine, Calculating a continuous analytical curve for every single rigid body requires too much processing time. Computation forces a discrete, numerical approach. The continuous curve is chopped into tiny time segments, delta t. Rather than solving the entire future path, the engine calculates a new particular solution frame by frame, continuously integrating kinematic equations for velocity and acceleration using numerical methods. Computational physics trades mathematical perfection for discrete, iterative approximations. By stepping through time, engines achieve real-time rendering and dynamic interaction. Whether an engineer is plotting a continuous analytical curve or coding discrete numerical steps, relying on manual hand calculation is slow and highly prone to error. To verify our work efficiently, we turn to Python's SymPy library, the standard for symbolic algebraic computation. Within the script, we declare our mathematical symbols and specify the derivatives just as we would write them on paper. We then run the core operation. We take a proposed test solution and use the substitution method to plug it directly back into the algebraic structure of the differential equation. If the programmatic output simplifies to exactly 0, it verifies that the algebraic logic is completely sound. Establishing this verification step early keeps your scripts modular and guarantees notebook readiness before moving on to massive system builds. To construct these systems, you must first define their boundaries by identifying the order and degree of the governing equations. You then collapse the theoretical potential into reality by applying boundary conditions to find the particular solution. We apply this exact progression whether we are establishing orbital trajectories, managing circuit voltages, or rendering digital collisions. Differential equations are the programmable language that dictates how the physical universe changes.